Okay, let's try to use maybe the ratio test to see if this series is absolutely convergent. Okay, so we're going to start off with figuring out a sub n. So a sub n is going to be negative 1 to the n times the square root of n over n plus 1. And now a sub n plus 1 is going to be equal to, let's see here, negative 1 to the n plus 1 times the square root of n plus 1 over n plus 2. Now how did I get that? Everywhere I see n, I replace it with n plus 1, right? So in the denominator, the n plus 1 is going to turn into, that's going to be n plus 1 plus 1. So then I'll have n plus 2. Okay. Now let's look at the ratio. So a sub n plus 1 over a sub n is going to be negative 1 to the n plus 1 times the square root of n plus 1 divided by n plus 2. Okay, and then negative 1 to the n, square root of n plus 1. So I kind of combined in two steps. Let me actually not combine them. So this is just to show you every little step that we do. So in the numerator, I'll have negative 1 to the n plus 1 times the square root of n plus 1 divided by n plus 2. And in the denominator, I'll have negative 1 to the power of n times the square root of n divided by n plus 1. Right? And then I can multiply by the reciprocals, and I end up getting what I had before, which is negative 1 to the n plus 1 times the square root of, I'm going to run out of space. So I get is equal to negative 1 to the n plus 1 times the square root of n plus 1 divided by n plus 2 times negative 1 to the n times the square root of n. And then in the numerator, I need an n plus 1, a factor of n plus 1. Okay, now it's time to cancel. Negative 1 to the n is going to cancel with negative 1 to the n plus 1. Now I'll just be left with negative 1. And now, if we rewrite this, we'll just have negative, and I'll have the square root of n plus 1 over the square root of n times n plus 1 over n plus 2. Okay? So, L, which is equal to the limit as n goes to infinity, a sub n plus 1 over a sub n, absolute value, we should get the limit as n goes to infinity of the absolute value of negative square root of n plus 1 over square root of n times n plus 1 over n plus 2. Okay? And we get the limit as n goes to infinity. When we take the square root and we combine, we should have n plus 1 over n times n plus 1 over n plus 2. Okay, so remember n is a positive number, positive integer. So when we take the absolute value of n plus 1, it's still going to be a positive number. Same with n plus 2, and the same with the square roots. Now, what is this limit? Well, as n goes to infinity, this term is going to go to 1, right? And then what's going to happen here, this is going to go to essentially the square root of 1. So we're in a situation where L is equal to 1. So since L is equal to 1, we have to try another test. Okay, so now looking back at our series here, negative 1, let's see, maybe we can copy. Maybe we can try to do an analysis just by looking at the terms. So first, let's see if it is absolutely convergent. So the question is going to be, is our series absolutely convergent? And the answer is, well, we need to look at the series with the absolute value of the term. So if we have the absolute value of negative 1 to the n times the square root of n over n plus 1, this will be the same as just the square root of n over n plus 1. Because when we take the absolute value of negative 1 to the n, that's going to just equal 1. Okay. Now, does this series converge or diverge? Right? If this series converges, so if this series, square root of n over n plus 1, converges, then our original series is absolutely convergent. Right? And if this series diverges, then our original series can't be absolutely convergent. Maybe it's conditionally convergent. Maybe it is divergent. So we're essentially trying to figure out if we can eliminate absolutely convergent as an option. And in this case we can, because our series square root of n over n plus 1 is going to diverge. Why? Well, there are several different ways you can test it, several different tests you can use. The easiest one, I think, is to just use a limit comparison test with, now here's the question, what does this look like? This series should remind us of just square root of n over n, right? Because when n is large, that 1 in the denominator, becomes very insignificant. And now on the right, what we have is actually a p-series. So 1 over square root of n, which is the same thing as 1 over n to the 1/2, which is a p-series with p equals 1/2. So this series diverges, right? So since this series...
11:45.
Thank you. So since this series diverges, and our series is similar to this series, our series is going to diverge as well. So we'll do limit comparison test with 1 over n to the 1/2. Okay. Let me add it. So you should check at this stage, you should verify that this series, square root of n over n plus 1, is divergent using the limit comparison test with 1 over square root of n. Right, so you should verify that. I just talked through it, but you should make sure you do it. So since our series, square root of n over n plus 1, is divergent, we know that the original series, negative 1 to the n, square root of n over n plus 1, is either conditionally convergent or divergent. So, how do we tell if it's conditionally convergent? We need to see if this series converges just by itself. Best way to do that is to use alternating series test. So let's use the alternating series test to see if our series, negative 1 to the n, square root of n, over n plus 1, is convergent. Because remember, conditionally convergent means the series converges, but when you take the absolute value of the terms, that new series diverges. Okay. So when we use the alternating series test, we should be able to see that it actually does converge. Okay, so you should verify that the series -1 to the n square root of n over n plus 1 converges by the alternating series test. So our final answer is that this series is going to be conditionally convergent because our first attempt at using the ratio test failed. L was equal to 1. And we said, well, the value we'll get this series here is going to be a comparison test, right? So we compared it to series 1. So diagonal series is not absolutely alternating series test to show that. So the series must be conditionally convergent.